Good morning, everybody. My name's Jane Wheelwright and I work for Dynamic Graphics. And today I'm going to be showing CoVis 4D, our co-visualization and analytical software. Normally I would be showing a lot of general subsurface data looking at reservoir simulation, seismic and wells. What I wanted to do today was to show the integration and visualization of emerging technologies in exploration and production. So look at some of the new data types that have become available. Work in the oil and gas industry has traditionally been based on data gathering from seismic and wells and subsequent geologic and reservoir models. And it's only really relatively recently that the value of integrating such data to best understand a reservoir and its changes over time has been truly recognised. So it's very good seeing a talk like Kieran's, which is showing an integration of data. The new technologies under discussion today they provide very valuable additional input, but it's very important that this data, whether it comes from satellites, vehicles, outcrops or wells, as well as standing in its own right, can be integrated in the same way with existing workflows. So what I'd like to do this morning is to take a look at some of the new data types and present them in an integrated 4D visualization environment using CoVis, which I think provides a much more powerful and effective way of utilizing the new technology than using them in isolation. So, to introduce, a key thing with these new technologies is the capability to actually visualize the new data types, and also to be able to integrate the old, more traditional types of data with the new. And I think that's going to bring about the most effective way of utilizing these new systems. The new technologies I'm going to show today, I want to go through an example with a remotely piloted aircraft, an RPA, look at vehicle tracking, fiber optics, microseismic and fracture models, and also look at some multispectral data. One of the key issues with showing any data from the oil and gas business is data is often proprietary. So I'm going to apologise in advance that some of these data sets aren't specifically oil and gas related, but they have huge application in the oil and gas business. So I think it's quite key to be able to see what can be done and how it can be applied within our business. It's always, in fact, I've worked recently with a couple of very interesting data sets which we're not going to be able to show. One is the fiber optics, and in fact I'd hope to be able to show some data live, some fiber optic data. And we've been working with BP in Stavanger, and they've been very impressed with what they can achieve with fiber optics. But the data cannot be shown here, so I'm certainly looking forward to the OptiSense talk this afternoon. What I can say is that we are able to read the fiber optic data, and I think it shows huge promise in terms of use within the industry. So I'm going to start, the first data set I'm going to look at is basically collected from a remotely piloted aircraft. And I think the use of these RPAs is going to increase. There are multiple applications, there are multiple ways in which the data can be used. So the data collected from RPAs can be used to monitor and survey, for example, wells and pipelines. One of the key applications is in the inspection of potentially hazardous events such as flares. So by using a drone, you can send it to places that you couldn't send any human personnel. It's also useful for picking up gravity, magnetic and seismic surveys, as well as LiDAR and digital elevation models. But the bottom line, and I think the reason why it will be taken up, is that it's very cost effective. It avoids using expensive satellite imagery, and the drones can be programmed to just collect data over an area of interest. So it can be very much targeted to where the data is required. As I mentioned, not all my data samples are going to be oil and gas specific. I'm going to be showing an EB drone data set from SenseFly. And in actual fact, working at BP, there are users there using EB data for to look at rock outcrops. And this information has now been integrated with other data in CODA's projects. But again, the data is proprietary, so I'm just going to show how it works and give an example. So the example that I'm showing is a geolocated orthophoto mosaic. It actually consists of 297 TIFF files which have been amalgamated together. It includes a temporal flight path, and the flight path obviously is based around an aircraft, but a similar type of path can be used on the surface or subsurface. So it could be used, for example, in looking at a well. It could be used as the drill bit to see where a well is being drilled in real time. It also, this particular EB flight, as well as collecting the photographs and including the flight path, it also collected a LiDAR cloud data and built the digital surface model. It includes a frustum which shows where the area of where the photos were actually taken. And this particular data set is Melischaken. It's a small village on the northern shore of Lake Lucerne in Switzerland. So I'm just going to do the starting demo here. So the initial display shows the end of data collection. So I'm giving actually a live demo showing the data. So what you can see here, if you look at the panel on the right hand side, there's a selection of different data types. We have a digital surface model, we have the orthophoto mosaic, which is the compilation of each individual photo, the flight path. We also have a series. We have one or two technical personnel who have too much time on their hands, so we have a smart car, which I'll show you in a Ford Anglia. We've got the frustrums and the center, but the key thing here is the integration of the different data. I'll just zoom in quickly. I'll have to show you the Ford Anglia. So if we zoom in here, you can see Ford Anglia and the smart car and the individual people as well. So this is a way that you can combine additional. These particular figures have come from Google SketchUp, but it's very easy to add the different data sets. One of the key parts of COVIS is the capability to work in 4D. So what I want to do is take this data set back to 0 point and now animate through time. So what we're seeing now is the actual time of when the flight launched and took place. So the initial loops are where the drone is orientating and the GPS is kicking in. And then it is moving away to onto its preordained flight path. So this flight path is programmed into the drone in advance, and the plane will follow it. With the flight path itself, what we're looking at in terms of visibility is we're looking at the pitch, but we can also color the flight path by airspeed, or by flight length, or by flight heading. So there's a number of different ways of actually displaying the data. What you're seeing now is the first frustum. So these are where the images are, the individual photographs are being taken. And you can follow the flight path through and see exactly when the data is collected. So this particular flight path is generating all the data that you're actually seeing visible on the surface. So the collection of data includes the LiDAR data, so you have bathymetry and the topographic information. What I would mention is that in terms of LiDAR, we display a lot of different LiDAR data, and the tools available to visualize LiDAR data have increased considerably. So that, for example, if you're dealing with houses in this particular data set, the roofs are very well represented, but the sides of the buildings are not perfect. There are now tools available to cleverly define the sides of buildings. If you're dealing with any vegetation, to set up tree trunks and canopy. So it's become a very, very sophisticated way of showing data. So this is the data set gaily going on its way. I just want to show a slightly different way of looking at the data here. So rather than looking at the data from a distance, we're now following the flight path of the drone. And you can see exactly where the effects of the microseismic are occurring. So this is just a really useful way of showing how valuable that 4D component is when you're dealing with hydraulic fracturing. So I'm just going to move to the next slide. So one of the other options that you have available is to incorporate production data. So this is this sample shows the production values, the concentration, the number of events, and the rate at the same time. So the production curve that you see at the bottom is related to what you're seeing in the viewer. So we're looking at the first stage and are able to see this production value. And in addition to looking at, I want to just also post, so we have log information that relates to these microseismic events. So I can also show in this case we've got a binary log, but I can also put on other log data, if I can find, sorry, I just need to find it. So if we put on the log data here, we're also able to generate lathe plots. So the logs that we have available, I'm just going to go to the tube display, are here, and I'm just going to show the row B and apply a lathe plot. So what we have for any of the different logs in the that are represented in the data set, we've got the option to show them as lathe plots or to show them as binary curves. So again, the key thing is the interaction and the integration of the data, the different data sets. So again, if we go back to the first step and animate through time, you can see the effect of the fracking events. So in context, so all this data is actually being viewed in context. And we also have a fracture model, which is a model of fluid propagation generated from MFRAC, which is a Myers Group program. What this does is it displays in real time with the microseismic display as these data are processed in the field. So the key thing is that this can be done at the same time as the fracking is taking place. So the frac model can be refined based on the pressure response of the formation observed during the fracture treatment. So I'm just going to start by showing you the frac model. So what we have here is the fracking events, the listening monitor. If I start the animation over time, so this is the model prediction of the seismic events. So you can see over time where it is presumed the effect of the fracking process will affect the surrounding rock. So this is a really useful starting point in terms of determining what best practice or what best operating is going to be used for this particular model. If we move on to the next slide, this shows the model in conjunction with the actually observed events. So this is again happening in real time. So we're seeing the predictive model, but we're also now seeing the recorded seismic events and the ellipsoids showing where the effect is. So there's a certain degree of correlation, but the actual seismic events, the microseismic events, are not perfectly aligned to where the model was predicting. So what this enables is actually during the fracking process to adjust the model based on the observed events, and to use that information to refine the process. So this can be done in conjunction with all the production data as well. So the key thing here is, again, it's integration of a model and the actual events in real time. So multispectral data. Again, an oil and gas example would be very nice, but the data that we have available, which is free to show, is from Lake Tahoe. It's based around a multispectral Landsat image, which we've seen an increasing usage of in the last 18 months or so. So in this instance, a multispectral scanner collects visible near-infrared, shortwave, and thermal infrared frequency bands. And modifying these color bands highlights features and surface changes not visible with a single spectrum. So you're not seeing the data as you would with your eye. You're able to pick out other features based on modifying these frequency bands. So as an oil and gas example, it could be used to find ore deposits, since the clay cap to a porphyry system can stand out under different wavelengths. So I can see the multispectral Landsat image again being used very much in an exploration environment, where it can show information that you're not going to be able to pick up from pure satellite imagery alone. So one of we've already seen the Ford Anglia and the other data, but we can actually add extra data here if we want. So I'm just going to put in a KMZ file, which we'll have a look at in a second, and close the data registry. Sorry, I'm just going to change to, I'm working with a lot of different projects, so I'm just going to make sure I've got the correct one. So this data is from California in Lake Tahoe. What you're seeing here are ski resorts, Lake Tahoe with the daily lake level represented as a production tower. So production data in an oil and gas context would be represented by towers. All these towers can be used to generate 2D plots and temporal pie charts as well. And we also have our Landsat, our multispectral data with the major roads. So on the render tab here, we've got, at the moment, we're looking at layer 2, 4, and 6. If we adjust the color bars, if I move the green, you'll see the color changing. And what you're seeing now here is the white, or the light blue represents snow, and the dark blue represents the lake levels. I'm just going to show the 4D side, because one of the key things with this particular data set is looking at changes in the lake level over time, which is what you're able to see. One of the other uses with, so this multispectral data has a lot of application in agriculture, and I think also in military applications, but certainly in exploration too. If I move the red color band to 4, what we're seeing in red now is the vegetation. So it's a very easy way of picking up what is good vegetation. What it also shows you in the red areas here are the golf courses. So it does mean that if you go out and purchase a set of Landsat imagery, you can probably use it for exploration in terms of oil and gas, and you can find where to play golf at the weekend too. So it is a multi. It has a number of different uses. So, in conclusion, what I think today is very useful for is to showcase some of the innovative and sustainable new technologies. And I think the key thing, particularly looking at the agenda for this afternoon, is that there are huge potential technical and economic ramifications in exploration and production by deploying these new technologies. There are some key issues, though. I think an important part of using new technologies is that there is making sure that the capabilities are recognized, actually disseminating the information about them, and that they're used and used effectively. But I think it's also very important that the results are integrated with existing workflows to consolidate their value. Taking information and using it as standalone is not the way forward. I saw an interesting article in the Digital Energy Journal just a couple of weeks ago, which asked the question, what is the most exciting innovation you've seen in IO this year? And Frans van den Berg from Shell highlighted acoustic fibre optics and flying machines. And Peter Captain, the CTO of Sierra Oil and Gas, again picked out fibre optics. So I think there is movement in the business in terms of understanding that there are big advantages of using this new technology. And the key thing is just to use it effectively. Thank you very much.
Thank you, Jane. Any questions for Jane? Let me ask you, when you're looking at vegetation variations, I mean, you showed a couple of examples at the end, but there's a whole lot of literature from the US and some from Russia as well, which says that, oil and gas fields leak a bit, and therefore they affect the vegetation. So you get different reflectivity of leaves and stuff like that. What are the most effective selections you can make? Is it what you show, just the colour?
Well, it depends on the Landsat that you've got collected, but actually there's an increasing amount available, and it can show a whole set of different surface characteristics, which you couldn't see with the naked eye with the normal colour band. And I mean, in terms of sort of 3D multispectral, it's the sort of thing that FFA are doing with geoteric, and they're able to identify key elements in seismic which you would not see by standard amplitude alone. So I think the 2D is really useful for looking at anything on the surface. So looking, I think it has a big part to play in exploration. But also, yes, in terms of looking at the effects of oil and gas exploration and production, and showing in a far more definitive way than you would by normal satellite alone.
Okay, and much less expensive than satellite.
Well, yes, yeah.
Anybody else? Okay, good. Jane, thanks very much.
Thank you.